I'm going to talk about the Alice 4 retro tablet. It looks like this. So my friend Bart Grantham, back there in blue, and I built this a couple years ago. And I'm going to talk about what led up to it and what's in it, sort of a very high level, because kind of touched a lot of things all at once. So it looks like this. Here, that was a YouTube just in case like this thing didn't work. Okay, background of the Alice project. So Brad and I met in Virginia Tech, '91. At the time, he and a friend of his, Alan Briggs, had decided that we were computer science majors. And another computer science major decided that they were going to make a graphics workstation. So this is like early 90s, 91. PCs didn't have GPUs or anything like that. So if you wanted to do any kind of 3D graphics in real time, you had to buy a 3D workstation. And so they were going to make their own, which like in retrospect is like, that's totally crazy. I don't know. Like at the time, it was totally impossible for hobbyists to do that sort of thing. There was a Motorola chip called the 88110, which is super like hip at the time. So they were going to base it on that, went nowhere, that chip. That machine was never built, but part of the thinking was, well, we need to like, at some point, after we build the machine, we're going to have to port Unix to it. So let's practice that. And at the time, Unix was entirely closed source. Like people forget, but like Linux was like 91-ish. BSD was closed source and AT&T was closed source. So right that year, Berkeley released Net2, the Net2 release of the BSD source code. And so Brad and I ported BSD to the Mac 2 because we all had Mac 2s because that was required for school. So I spent a summer in his basement, and we ported to the thing. And that actually became, that was folded back into NetBSD and became the Mac 68K port of NetBSD. And it's still active. Like there's still a mailing list, and last week people were posting to it still. So it's, I like, can't believe people are still using this stuff. So that was the beginning of sort of the Alice project as a thing. Brad flies out to California, builds the Alice 1, which is like a Z80, ROM, and RAM, and a 7-segment display. And when you plug in power, the 7-segment display says code is code, and that's it. That's the only thing you press. So pretty boring, but an awesome jump into it. I move out. We start working on the Alice 2, which is like second systems effect, if you know what that is. It's like, okay, now we know what we're doing. We're going to make it modular, and we got like a rack mount thing and the boards, and we're making our own boards with the ironing thing and like and etching and acids and drilling 100 holes. And it's like, so it's a lot like what you were saying about the Alto, where like every time you boot it up, like it doesn't work, and you have to go like figure out what's happened. It looked like that. So that's it right here, the rack mount thing that we got at weird stuff, and we made all the boards. We got a video display to work, like actual video. It was kind of crazy, but it never worked very well. So the key thing about this is like, okay, so there were two problems with the Alice 2. A small problem and a big problem. And the small problem is it didn't work because it like all these solder problems and everything. The big problem is when it did work, there was nothing to run on it. Like it would get it up to work. Like there's no software, right? So like, because like, so now you've done all this work for years and years, and you've got the software, and now like now you have to spend years and years writing the software. So that kind of sucked. 15 years later, 17 years later, Brad is like has this thing on his shelf. He's like, Lawrence, I don't want this anymore. I want to like back it over with my truck. Do you want it? And I said, let's spend 10 minutes getting it to work. So like 4 hours later, we're still like trying to get it to work. And then we start to think about like maybe we could replace the boards and stuff like that and use modern manufacturing techniques. Sooner or later, like we simplified, we're going to put it on one board, we're going to change the bus, we're going to do all this stuff. And the Alice 3 is born, which is a single, oh, it's not here. But it's like it's a single board Z80 machine with a real Z80, ROM and RAM, an arm and a propeller for video. Bart did a bunch of cool stuff with audio on it. So like when you boot it, it actually has a boot sound, like it goes whoop, which is so cool. Like, and like we designed a computer that has an actual boot beep. This was the sort of progress real quick. This was like prototyping everything on solderless boards. We made a through-hole version, and we made a surface mount version. So this was all like our learning how to do hardware. The key thing, and this was like Brad's genius, is like from the beginning he said this has to run CP/M. CP/M is like late 70s operating system, was ported to a zillion Z80 machines, and because it was ported to everything, there were a zillion bits of software written for it. So now we have this thing, we get it to work, and then instantly we can boot not only CP/M, but then there are just thousands of programs online for it. So we can play chess, and we can like there's word processors and there's compilers, and like Turbo Pascal was running on it. So suddenly like we can do all this cool stuff with it, and that was super important to our process of like learning what retro computing is like. It's like you can't just do the hardware. You need to you need to have it be leveraged, basically, with all the history of it. So what's next? So we thought, what do we want out of the next project? So this is like, so maybe the LS3, maybe one of these days, Brad or Bart can talk about it. But it's a kind of a cool project in itself. I don't know if, I'll give away a little hint, like one of those chips is missing, and it still works. So like if you can get your computer to work with 25% of your chips missing, it's pretty good. But like, yeah, it's the RAM. I won't give away the ending. But for LS4, we're like, what do we want? So nostalgic value, I don't think I have to explain to anybody in this room why that's important. Leverage existing code, that was a CPM lesson. After we're done with the hardware, we need to be able to immediately use stuff. Brad and I are both graphics geeks, all the way going back. That's actually how we met in college, is like we're both interested in graphics. So something graphical would be cool. Brad at the time worked at ARM, so he wanted to do more with the ARM chip. There was an ARM chip on the LS3, but he wanted to do a lot more, like how do you do bring up and how do you run Linux on it and stuff like that. We want to learn some more about power management because that's sort of analog, because we're sort of digital geeks, so maybe we learn more about analog and charging batteries and that sort of thing. And personally, I want to learn about how to program FPGAs. So those are the goals. So just real quick, what is an FPGA? So FPGA is sort of like hybrid between an ASIC, which is totally hard-coded to do a certain thing, and a CPU, which can do anything at all, but has to do it sort of like one at a time because it's too general to do some things kind of all at once. And it's kind of a crazy idea. The idea is that you've got a super simple thing called like a logic element, or they're different names for it, but basically a very small programmable thing with a small lookup table, a full adder, a data flip-flop, and it's super, super simple. It can do almost nothing at all, but you put tens of thousands of them on a chip. And then you program all of these lookup tables and all this routing between them, and you can do anything at all. Like you can do a lot of really cool stuff, like make CPUs and stuff within it, because it's this really simple thing that's just reproduced tens of thousands of times. It's really good for parallel work. It's really good for video. In fact, any kind of streaming thing is really good when you're going to stream a lot of stuff. Like if you have to take like 15 audio signals and mix them, or video signals and mix them, because it can do all this work in parallel. It doesn't have to like change its time. You just do stuff in parallel directly on it. And then some of these things have like built-in RAM and phase lock loops, and they're super cheap. Like they used to be really expensive, but now you can get these dev boards for a good one is $100. You can get a low-end one for like 20 bucks. That's like you still get us like 60,000 on one of these really low-end boards, meaning that you can get what's called a soft CPU on there. So it's incredible what you can get for almost nothing nowadays. And I was interested in it because I just want to move a little bit past software, but in a way that didn't require soldering and having cold solder joints and stuff. Okay. Should I what is it saying? Okay. Quick aside on Silicon Graphics. So Silicon Graphics was a company that was founded in '81 by Jim Clark. Jim Clark was a Stanford professor. He later went on to found Netscape with Mark Andreessen. By the time in '81, he said this is the time for graphics workstation. Again, like, there were no good graphics workstations at the time. It was the best, certainly the most famous graphics workstation company. Somebody heard of SGI? I don't know how much people, yes? Okay, good, all right. Because like I asked this question a while ago, and like nobody knew what SGI was. So it depends on the thing. Okay, so they had a graphics library, like an API for doing graphics called IrisGL, and then they later invented, they put everything that they learned from IrisGL into OpenGL, and which of course is super popular now, is everywhere. And IrisGL is very old. I think early 90s maybe is when they stopped using it, so like nobody uses it, there's no libraries, it's totally dead. And basically in the 90s, PCs started getting a bunch of GPUs, so they just totally went out of business. They totally missed the whole low-end thing, and just PCs came up from below and ate them alive. But crucially, the thing about SGIs is that they had demos. So they had this really cool window manager, and in the upper left there was this like menuing thing, and there was a demos thing. And everybody who used an SGI at all, from like mid-'80s to mid-'90s, saw that thing, and they had the same demos across that whole decade. And they got a little bit better. They added like texture mapping and a few other things, but it was the same demos over and over again. So if you worked at SGI or had an SGI or anything like that is sort of like burned into your retina, and you've got sort of like this nostalgic thing about these demos. Brad worked at SGI for 5 years?
4 years, twice.
Okay, so 8 years? Okay. I worked at SGI as an intern, and then I used SGI for many years when I was at DreamWorks. So we all have like nostalgic value with SGI. It's graphical. You can see where all this is going. So this is sort of the screenshots of some of the demos. This was a menu for the demos. You clicked on these buttons and it would run the demos. This is a famous one called Insect. And then a Jello thing that bounces around and a bunch of other things. But this is the kind of stuff that they're doing. So here's the idea for Alice 4. We're going to make a graphical tablet that does nothing but run mid-80s SGI demos. That's it. I was like, so it hits everything, right? It's got nostalgia of SGI. We can leverage all this existing demo code. I'm going to learn the FPGA because the graphics part of it, the graphics pipeline is going to be, well, the pixel part of the graphics pipeline is going to be in FPGA. It's going to be graphical. The non-graphics pipeline, so the vertex part of it, is the part that actually runs the demos, is going to be on the ARM. And then, of course, it's going to be a tablet, so we're going to learn about batteries. So that was awesome. I made that little sketch, which turned out to be really useful. Like, it totally, like, you can see, like, Insect running on there. But it was sort of the idea. We're going to have a little joystick and some buttons, and it was sort of the idea. And it turned out more or less like that. We got rid of the joystick because it turns out accelerometer works pretty great for that. Plus, it's a touchscreen. OK, so I want to give you a sense of the timeline, because, like, sometimes I watch these other projects, I'm like, was this a month? Was this like 2 years? What happened? Like, how did the project play out, right? So I kind of want to give you a sense. Brad and I were exchanging emails about the Alice 3 and what to do with the Alice 3 and how to improve it, 3.5 we were calling it. And absolutely out of nowhere, in the middle of this thread, I write to him, how about we run late 80s SGI demo software in ISGL and ARM does the software in FPGA for Esther. Like, completely out of nowhere, this line comes out. And we're like, yes, totally instantly, we're going to do this. The division of labor is super clear. He's going to do the front end, I'm going to do the back end. Within a few days, we found the demos online in C as a C source code. So we're not emulating the SGI machine. We've got the C hardware, the C source code, and we're just running it in Linux. So within like a couple days, we have it checked in. 2 days later, Brad writes the IRSGL library. So this is the library that the C programs expect to link to. So they're calling like draw triangle and clear the screen and set this color. So there's nothing out there which emulates this. This is not like OpenGL, which is used everywhere. Nobody knows about IRSGL, so he had to write all this himself. He's doing this on a Saturday. I'm camping. I've got major FOMO. I'm like, Jesus, you're going to finish this by Sunday. Luckily, I'm at a KOA, right? So it's like camping with a K. And so I get into my cabin, which has Wi-Fi, my laptop, and I write, so not an FPGA simulator, that's not like a low-level thing, but basically a Mac OS program that takes what he outputs and actually draws it and does what the FPGA will do, like the rasterization and drawing the pixels and stuff like that. So within a couple hours, we have Insect like actually walking around with a mouse and everything like that. That was mind-blowing. A week later, I start on the FPGA. Now there's a huge gap right here, and I don't remember what happened. But I think basically, like our original idea was to follow on the thing that we had done with Alice 3, where we made our own boards. Alice 3, we actually like, designed our own boards and did it in KiCad and like made it manufactured and put them in the toaster oven and stuff to do the stuff. And we were going to do that with this too, get an FPGA chip and an ARM chip and a memory chip and have all that thing. But it was overwhelming because the FPGAs, for example, are really good partly because they have 1 million pins. And so they're all on the very bottom of the chip. So they use this chip kind of called a BGA, a ball grid array, which is really hard to solder. Then high-speed memory is really hard to deal with because it's so speed, like the signals have to be all the same length, so they all arrive at the same time. It's way past what we could do. And then, so we kind of get stuck and get bogged down. In January, we decide to switch to, oh, I should have brought it, a pre-made dev board. And this is the great part. This is like totally unstuck us all. We used I'll get into more of the details later, but basically this is a $100 board from this Taiwanese company that has all of that in it. Yeah.
If you want, we'll open one.
Oh yeah, well, I've got a wrench, so we'll open one of these later and we'll check it out. But basically, it's got the FPGA on it, memory, and all the cool stuff. Crucially, it's got a new kind of FPGA that has an ARM on it. So we don't have to coordinate between the ARM and that has to talk to memory or something, or that has to communicate somehow with the FPGA and all this other nonsense. I had this like huge diagram of like the ARM and the communication and coordination between the two and how all this is going to happen. But no, like they stick a dual core ARM right on the chip. So you just boot Linux right on that ARM, and you can talk right to the FPGA effortlessly. So instead of doing all this hardware ourselves, which is way above what we could do, we just decided we're just going to embed this dev board straight into this thing. And it doesn't do stuff like battery or LCD. So a few other boards that we got from Adafruit, we're just going to stick on the side. But the core of it is that. That unblocked everything. In July, the last of the check-in was done, and on August 5th, we did Vintage Computer Festival West here at the Computer History Museum. So yeah, a little over a year. To give you a sense of sort of the coordination between the two sides of the project, so that the whole thing can be broken into two parts. This is Brad's part and my part. So we got Linux on the ARM, on the dual-core ARM, and this is like just like booting on the regular ARM. It runs the C demos. They call Brad's IrisGL library. IrisGL, so the demos say stuff like draw triangle, clear the screen, set this color, set the Z depth, and all this other stuff. Brad's library takes all that, takes all the 3D coordinates, clips them to the thing, transforms them, does all the lighting, squishes them to 2D, and then makes a long list of two-dimensional triangles on the screen. Like this is this, and the vertices are different colors and stuff, but it's a long list of 2D triangles. So it's all working at the vertex level. It doesn't care about the actual pixels. It's just transforming vertices and doing vertices. I forgot to mention, by the way, just if you want to ask a question, just interrupt right away. It's easier for me than to go back at the end. So don't hesitate to ask. So that's all the per vertex work. It sticks everything into memory. And then there's a 32-bit register, which is accessible by both the ARM and the FPGA. And it sets a bit saying, I'm done. And then the FPGA, meanwhile, is looking at this bit and says, good, and goes to memory and looks through the triangle list and goes for each triangle, goes through, figures out all the pixels that are on, and draws them into an internal frame buffer and scans that out to the LCD. Yeah, so we got this great LCD. It's a touch panel LCD, and then you just like hook it up like that to your FPGA. I'll open it up later, and we can see all that. So it's constantly scanning out to the LCD. The LCD is not, it doesn't have any memory. It's not like some of these things where you can just sort of draw stuff and then let go and it keeps it. Like you have to, it's more like an old style CPU, CRT, and you have to just update it all the time. Okay, so that's the basic breakdown. Just real quick how rasterization works. So the idea is you've got a triangle, and you want to find out what, of all the pixels on the screen, do I need to draw for this triangle? So and there are lots of different ways of doing this, but the way that we picked, mostly because it's simple, is that you come up with an equation for each edge. So the equation is like a math equation, and for any xy coordinate, you can plug it into the equation. It'll give you 0 if it's on the edge, and a negative number if it's on one side, and a positive number if it's on the other. So you can see right here, if it's positive, it's inside. So for every xy coordinate on the screen, every pixel, you plug it into all three equations. If all three are positive, then you're on the inside of all edges, and you're inside the triangle. If it's negative anywhere, then you're outside, and then so you don't draw anything. So you go through all the pixels, and you say which ones are inside and which ones are outside. It's kind of a waste to do the whole screen, mostly because triangles tend to be really small. So typically, you just calculate the bounding box of the triangle, and you just go through the bounding box. The FPGA works at 50 megahertz, so I do 2 pixels per clock. So I go, yeah, it goes like this, like that. In fact, you could have more, because it's all in FPGA. Like you can just instantiate more. I'll talk a bit about that later. It's kind of neat. But I do 2 pixels at a time. So I'm inspecting 100 million pixels per second. But when you have a bounding box, like you can look at there, like at least half the triangles are going to be outside. Half the pixels are going to be outside the triangle. So it's kind of a waste. You're doing a lot of work for not drawing a pixel. So in practice, you get about 50 million pixels per second drawn. And we run at about 50 FPS. So it's about 1 million pixels per frame, which is a bit more than the size of the display. So we can fill up the display.
50 million pixels, visible pixels per second at what resolution?
This is 800 by 40?
Yeah, I think so.
800 by 40 is right, yeah.
24-bit color.
A 24-bit color, yeah, yeah. So we can probably fill every pixel twice, is my guess. Like if we had a because of 3D graphics, you have a lot of overlap, and you do a bunch of work that ends up being drawn over. So you kind of want you want a lot of spare room of capacity if you want to keep your. Well, yeah. So at the end, yes. So there's a slide on that. Okay, and then so the challenge really in the FPGA, and this was the biggest challenge in the whole thing, is to keep the pipeline busy because you're trying to get 100 million pixels processed per second. But there's so many places where it can block, and especially with RAM. In the olden days, in the good old days of static RAM, you asked RAM, like you put an address on the bus, and it said read, and then on the next clock you had your answer. And then now it's super complicated, where these RAM chips are really complicated. And you have to like go into a special mode and pass it a command and give it an address and the whole thing. And then it can take like dozens of clock cycles before you get it, or not, or it can take like 1 clock cycle. And the fact that it can be so variable is a real problem all the time, because if you don't do it well, then a lot of those 50 megahertz, you're just stalling on RAM. And so, yeah.
Did you compare this with any other like early hardware techniques? Like, if I understand correctly, like the Amiga used like a modified resonance line drawing algorithm, the single bits per line per line per the line, a single line,
Right.
and it effectively scanned and switched on and off to fill in.
Right.
And perhaps that doesn't work when you have 24-bit color depth.
No, it does. So the faster way of doing this, at least in the Amiga days for sure, the faster way of drawing a triangle is to find the topmost pixel and to find the 2 edges that come off of it, and then do the essentially Bresenhams or some kind of variation of that, and walk down the 2 lines simultaneously. And then now you know the endpoints of the horizontal thing, and then you blow through that line segment very quickly, as opposed to doing a bunch of tests every single pixel. You're like, okay, I know everything between these 2 things is drawn, and you just blow through it super quickly. And then when you get to like, and they go back and you end up at the bottom.
Don't necessarily do it like that. You read 16 bits at a time, and you would immediately know whether you hit the switch, you switch on, and then you just stay on until you hit the
Oh, the other side.
switch.
Okay. Okay.
It's similar.
Right. Yeah, exactly. And then so there are different trade-offs. Like that's more complicated, and I didn't want to do something complicated on my first FPGA. But also, there's a lot of overhead to doing that. And as a pixel gets smaller, what you gain from doing that goes down, because like, yeah, you can blow through, but if you're only blowing through 2 pixels, then you didn't really buy yourself much. So
if you're going cycle by cycle, then you want to remove as much overhead around each cycle as you can.
Yeah.
When you're in parallel, it makes some sense to just do everything all at once.
yeah,
All of it.
exactly. Yeah, yeah.
It's interesting because they stole the general concept, I think, from HP workstations.
Mm-hmm. Yeah.
Obviously, SGI won that.
Yeah.
One.
Yeah. So the dev board came with a gig of RAM, and just a rough breakdown. It's kind of interesting to know, but when you boot Linux, there's a flag you can give it to give the kernel when you boot it, which says how much RAM can I take. So instead of giving it all 1 gig, you give it like less, like in this case 900 megs, and then the rest it just won't touch. And then you, even from within Linux, are allowed to write outside of that by hitting memory directly. And as an FPGA, you're allowed to read from outside of that. So Linux on the ARM here was running on Linux, on the Linux part of it, and it was generating this triangle list in the command buffer on top. I call it a command buffer because it wasn't just triangles. It was stuff like clear the screen, draw a triangle, swap the buffer, and end. So draw this command buffer. The FPGA reads it. So there's 2 buffers here, and this is a graphics thing. But like, you don't want to be drawing to the buffer that you're drawing to that you're sending out to the LCD, because then you'll see tearing and you'll see partially drawn screens. So what you do is you have 2 of them, and one of them is the one you're showing, and the back buffer is the one that you're drawing into. So you clear the back buffer and you draw all the triangles, and you can take your time and do whatever you want to. When you're fully done, you atomically switch them right, at retrace, so that you never see any tearing. So there's a back buffer and a front buffer, and so the FPGA is writing to the back buffer, but at the same time, it's reading from the front buffer and sending out to the LCD. If you notice, there's a lot of arrows here for the FPGA to memory. There's like, it's reading the command buffer, reading and writing the depth buffer, which is like the Z buffer that tells you like what's in front. And that's, so I'll get back to that later, but that was a super cool part of this particular FPGA chip that I could not have done without. So what is this dev board? Dev board is, so there are a bunch of different FPGA manufacturers. The 2 big ones is Xilinx has about 55% of the market. Altera has about 35% of the market. And then, what? Lattice is the kind of the small one, but it has very low end stuff. And Lattice has also open source tools. Well, they don't have it, but people have figured out the binary format of Lattice, so you can get open source tools for it. So people who are sort of like into open source stuff tend to go for Lattice. And also all the low end stuff that I was talking about, like $20 boards, tend to be Lattice boards.
Altera is now Intel.
Yeah, that's right. They were bought by Intel. That's right. And so they make the chip, and then this company called Terastic, which is a Taiwanese company, takes them and makes these boards that is RAM and a bunch of other stuff. So that was called the DE0 Nano SoC. The new hotness, if you're interested, is the D10 Nano, which is even better. It's got a chip called the Cyclone 5, the Altera Cyclone 5 SoC. I'll talk about SoC in a minute. A lot of input and outputs, 80 I/O pins, which is great for just anything you want to do in terms of streaming, if you want to stream video or whatever, and a lot of other tools like the accelerometer and Ethernet.
It's also the same board that they use for the Mister now.
What is it, Mister?
The emulator, not emulator.
It's an Amiga.
No, the original Mist was for the Atari ST,
Okay.
which was based around like a low-end Cyclone, and then there's been like a massive revival where if you go to the GitHub repository for Mister, there must be a few dozen home computers and some arcade machines that now emulate it. It's actually a really great source for example
Okay.
RTL.
Okay. Cool.
Jim has one. We can take a look at it sometime.
Okay.
You're referring to D10, which by the way is $130.
So zooming in on the chip, on the FPGA chip itself, it's got 40,000 of these tiny little programmable things, which is quite a lot. Like you can, like I said earlier, you do a 68,000 in like under 10,000 of these things. So you can have like 4 or 5 68,000s of these things working in parallel, no problem. It's got RAM on board, which is great. It's got hard multipliers because you can imagine like these super simple things that just add one bit to one other bit. You can do multiplies on them, but you'll eat up a lot of these logic elements to do a simple like 16-bit multiply. So they'll just throw on a hard multiplier, which is actually a piece of hardware that just does 18 by 18 multiplying. 72, I blew through all of the 72. And it's got a phase lock loops if you want to change the clock. These boards typically come in with like 50 megahertz clock, but internally you can bump that up to anything you want to with a phase lock loop. And if you want to run at 100 or 200 megahertz, you can. Or if you want to put out a video source at a specific frequency, like if you want to put out 15 kilohertz, megahertz, whatever, you can do that. The dual core ARM running at a gigahertz didn't hurt either. That was awesome. And this is had a 4,000-page manual. It's like a PDF, and it's like comically large. It's just like it goes into extreme detail about every little memory location and every bit of everything with like lots and lots of detail. But it's all like bottom up, so it just tells you all the stuff, right? And you read it all, and you're like, okay, now I want to do this, and you have to figure out, okay, I have to use this port and I have to use this. They weren't very good about saying, okay, if you want to accomplish this, these are the 7 pieces you have to put together to get it to work. Like if you want to output video, or if you want to communicate with the ARM between the thing, like that was kind of hard to figure out how to do. But it's
Source,
yeah.
off-the-shelf
Bits and pieces
IP
that they
did you use?
the SDK or the Altera bits. So we use the Debian distribution that they give. And we
Yeah.
use the bootloader.
Yeah, they provide a bunch of stuff. Like between Altera and Jurassic, they provide everything you need to get started, because you can just it comes with a CD-ROM, and you can totally boot Linux, and then from there you can load FPGA, so you can see the whole pipeline going through. And
On the FPGA side, how much of the off-the-shelf IP did you use?
virtually none. No, yeah. This is a quick overview of the FPGA chip. Just roughly speaking, the orange part on top is the FPGA fabric itself. The kind of green square is the ARM. This giant thing is a huge switch. So SoC stands for System on a Chip, and the idea is like for a desktop, you're fine having a CPU that's just a CPU, and you can have a bunch of other chips for Ethernet or whatever else you want to do. But if you're going to make an embedded system, you can't have these 20 chips sitting around. So they make System on a Chip, which is that they stick the CPU and everything you need on the chip itself. So it's got like CAN bus and UARTs and timers and just like SPI and I2C and just everything you want to, they just stick in hardware. And this is part of the 3,800-page manual, is how to access all these things. And we didn't use most of that stuff. I think we used I2C maybe? I2C for some of the I/O stuff. And there's the magical memory controller. The memory controller was amazing because it talks to the 1 gig of RAM, which is actually talking to a synchronous DRAM is not easy. And it's like there's a whole protocol you have to do, and you to be efficient about it. And I wrote like a controller, didn't work very well. It's super pain. And that one does all the magic of doing that, but also exports 7 ports, which look like like the old school static RAM. So it's just like you put in an address, and you say, I want to read, and then you get your data back. And you may not get back like right away. Like there's a pin that says like, hold on, I'm getting it for you. But overall, it's super simple. And there's 7 of them. And they will worry about like, OK, I want to do a read and a write. And like, remember, all this is in parallel. So you could try a read and a write at the same time. And they'll figure it out. And they'll queue it all up and make it happen. One of the ports goes to the ARM. And then the rest of it I had free. So I was able to just, in my code, in my FPGA stuff, just say like, I want to read from the triangle buffer. Also, I want to be like reading from the front buffer, the video stuff, and sending out the LCD. And all that just worked. And all those reads and writes were interleaved. And I have some friends who are using a chip that does not have, like Keith is doing this. And he has to himself interleave memory access. And he has to make sure that these different parts of the FPGA don't clobber. And if you initiated a write, you have to wait for it to come back before you do a read. And like, you don't want to do that. So the memory controller was amazing. So how do you program an FPGA? So there are 40,000 of these things. You're not going to go in and set individual lookup tables. You're going to use a high-level language. HDL is hardware description language. There are 2 of them. They were both invented in the 80s, and the history is interesting. So in the 80s, all of this hardware, this is not FPGAs, this is pre-FPGAs, this is for like ASICs. All the hardware was designed by hand. So people would like actually like lay out transistors and do all this stuff by hand. And then when you were done, you had this mess of wires and transistors. And how are you going to document what you did? Well, you can't, that's not enough, right? And English is too sloppy. So independently, a private company and the government came up with the idea of designing a language that looked like a programming language that would just describe the way the hardware worked. So, but it was never meant to do anything other than be written by humans and read by humans. Like nobody thought it would actually be like parsed or whatever. So they're both broken in the same way, which is that like you can do, like it wasn't written with the idea that you would ever use it to actually make hardware. So you can describe all this hardware, which is not actually physically possible. So it's very bizarre. You can, on both of them, you learn how to write this code. And the first thing you learn is like, OK, here's the language. You have to restrict yourself to this. Because anything outside here does not actually map to real hardware. And you can do all this stuff that's not even possible, like write 2 different values to the same wire and stuff like that. It'll totally let you do that and write that in syntactically correct. And it might even compile, and it just won't do the right thing. Verilog, roughly speaking, is C-like. I get the impression that it was written by people who knew a lot about hardware, but knew nothing about programming language design. So the language kind of sucks. And the type system kind of sucks, but it's a pretty good mapping to hardware. Like you could see, like this is a register of 8 bits, and so I can sort of imagine 8 flip-flops or whatever. It's used a lot more in the US and Asia. All open source that I can find is Verilog. So totally Verilog is a way to go in general. It's just a terrible language. VHDL was the Department of Defense, so it's very Ada-like because they wanted to reuse a lot of the Ada stuff. The type system is quite good, so it's a lot easier to catch mistakes at compile time. But you get the impression that it was the opposite. Like it was software people who knew everything about language, but didn't really know much about hardware. So it doesn't. I've heard that it doesn't match very well. I don't know VHDL very well. And for some reason, it took off in Europe, even though it was a DoD language. Just to give you a taste of what it's like to write in Verilog. So this first statement here, this A equals B plus C. If you think about it from a programming language perspective, it's like there's a sense of time, right? The program's going along, and it gets to this line, and then the CPU gets B and gets C, which might be 2 like 8-bit numbers or whatever. There's this one adder, and it routes those 2 numbers through the one adder, and it gets the output and it writes it back to A. In Verilog, that's not what it means. And what it means in Verilog is make a physical adder, like that's permanently there all the time. Get whatever B is, which is let's say an 8-bit register. Get whatever C is, route them to the adder, and then whatever the output is, call that A. And that's what that means. So it's adding all the time, nonstop. And if you change B, as fast as those signals can propagate through the FPGA and get through this adder, A will change.
So does that mean if, I can't remember how many, so added, is there any support hardware there, or is it just straight from logical elements?
So for the adding, it would be the straight logical element. So each one has, let's say, usually like a 1-bit adder. So for this, you might use 8 of them because they each have, it's a full adder, so it's got a carry. So you would instantiate 8 of them and then hook up the carry across of them, and you would do the B and the C, and then whatever his output comes as A.
But if this was a multiplier, then all of a sudden you become a little bit scared how many multipliers
Yeah.
you have in the code.
Exactly. So if it was a multiply, and if they don't have hardware multipliers, then yeah, then suddenly that blows up to who knows how many adders you need to actually make a multiply out of. Or if they have a hardware multiplier, then that uses up one of them. So that sounds pretty good, except that A is not very clean. Like for example, you can imagine like, let's say B is 6 and C is 5. So A is 11. Okay, now you swap B and C. Well, that doesn't happen instantly. Like the bits might not change all at once for B and C, and it takes a while for the signals to propagate, and then the ripple carry has to go through and do the add. So if you look at A, it's not going to be like 11 consistently. It's going to be 11, and then a bunch of junk, and then 11 again. So you don't ever want to look at that, the output of, this is called a continuous assignment, because it's going to get kind of noisy and garbagey while the inputs are changing. And so for example, if you send A to like an output pin to your device, you're going to see spikes on it and see garbage on it instead of a nice clean signal. So instead, you want this code, which like this line looks similar. It's got a different assignment operator here. But it's the same thing. This part, B plus C, is exactly the same as on top. It does the exact same stuff. Takes B, takes C, routes them together into an adder, and the output is anonymous. It's not named, and just sits there. And then there's a separate thing called A, which is like, say, an 8-bit flip-flop, which is like sitting there, but because like the flip-flop doesn't accept the data till you hit it with a clock, at the positive edge of the clock, those anonymous signals are actually latched into A. And so when you change B and C, that happens between clocks, and all this noisy stuff that you get out of the adder goes nowhere. It just gets stuck, and right on the positive edge of the clock, everything gets settled, and you get a nice clean signal into it. And when I started FPGA programming, or before that, I kept on asking people who knew better, like, so what clock rate do you run FPGAs at? And they looked at me like, if you're asking that question, then you don't understand what an FPGA is. And now I understand what they meant by that, which is like, okay, how fast is this? Well, how fast is B plus C? Well, it's really fast. Like you could probably run this at many hundreds of megahertz. Not like the 3 gigahertz of an Intel, because that's like specifically made for that, because in here you've got this very generic fabric. But you can run this at hundreds of megahertz, no problem. But if you had a complex expression here, it might take a lot longer for the adds to get through, especially if you had a lot of adds, and they have to propagate through and do all this stuff, and multiplies maybe. So then you have to run it a lot lower. And what happens is that the tools that you use, the compiler, knows how fast that happens. And it knows how it laid it out, and it knows how far everything is, and knows how far everything has to propagate, and how fast it propagates through the adders, and all this stuff like that. So it knows this, and it knows how fast your clock is. And if you speed up your clock too much, and you do something too complicated here, like a big multiply, it'll tell you at compile time. It'll say that won't work. Like that will not finish computing by the time the positive edge of the clock comes on, and you'll get garbage in A. And so it's great. So you get told, so you can keep pushing your luck basically until you get told that that was not okay, and then you have to.
All logic on chip have to run at the same clock rate, or do you have different modules running at different rates?
You can have it running at different rates, and I've got a slide later about why that's not a good idea. But let's say in this case, let's say that B plus C was too complicated, and it was going to take, let's say, 1.5 clock cycles to do. What you would do here is you would have an if statement right over here saying like if the clock is odd or whatever, then latch it. So you would give yourself, so every other clock cycle you would just not latch anything, and you would latch every other one. You're allowed to latch every other one if you want to. And what it'll do is it'll say, like in practice, like literally you could write here like, if counter is odd, then do this. And then what it'll do is that if it's odd, it'll latch the sum into A, and if it's even, it'll latch A into A. And so you're always latching, because the clock is permanently attached to A. And the question is, where is it getting it from? So if it's disabled by an if statement, it'll just feed it back into itself, and the compiler does all that for you. This is kind of tongue-in-cheek, but basically when you learn how to program in software, you're told all these rules of thumb, like how to write good software. And it's like, don't have global variables, and don't take addresses of variables and spew them everywhere, and be careful of threads and all that stuff like that. And when you learn Verilog, it's like, no, it's all that stuff. So it's like you can imagine, like in programming language, let's say you have a function, right? You pass in a parameter, the function does its thing, and it gives you back your answer, and then you have your answer. The equivalent in Verilog is you've got a function, and you pass it the address of your parameters, and the address of where you want the answer to go. And it starts a thread to compute that, and then returns immediately. And at any time in the future, you can change your input variables and it'll magically like figure out the answer and stick the answer into the thing, like at any time. So you're looking at a variable, you have no idea, like, how is this going to get changed and when? And like there's, like the reason that we have all these rules in software is because you want the flow of data to be really clear. And you don't want global variables because you want to make sure, okay, this goes into here and it comes out here. And there's no clarity at all. Like you're just looking at the variable and like when is this going to get changed? And you have to really go through and dig down deep into these modules to find out. It's pretty painful all around. But I think that reflects sort of the nature of hardware. This is how hardware works. And I don't think you would want to abstract that away too much. In terms of compilers and tools, they all come with their own tools. Like Altera has Quartus Prime, and Xilinx has Vivado. They all have a free tier, and the free tier is totally fine for hobbyists. Like the advanced tiers is stuff like if you want to run it on like a 64-core machine, the compiler will run parallelized. You don't need that. So the free version is totally fine. They only run on Windows and Linux. There's no Mac version, I think, for any of them. And the Linux one is a bit like second rate. And so finally, after much fighting, I eventually figured out like you want like a fresh actual boot of Windows, not like a VM. I actually run boot camp, is that what it's called, on this and reboot into Windows, and that solved all my problems. So don't try to fight it. Like act like an actual hardware person who like goes to work and has an actual PC running Windows. That's what they all do. So do that because that's what the tool manufacturers are optimizing for.
So it gets a little worse too because if you're using the low end Xilinx,
Mm-hmm.
Spartan, the series like Spartan 5s, I think Spartan 4s. You don't use Vivado, you use ISE.
The old one, yeah.
That is a real pain in the ass to run on Linux because when you want to send the bit stream to the device, you need their device driver, which doesn't work on modern Linux.
Okay, yeah.
So you end up like hacking things to get the device drivers to function.
Right.
Very painful.
Yeah. Painful is the right term for a lot of this stuff. It's USB is kind of like doesn't always work, and all these other things. Speaking of Xilinx and Altera, at some point we're like, well, which chip should we go for? And I asked around, and I asked Keith, and I asked a bunch of other people, and basically the answer was that they're all terrible. And Xilinx seemed to have more books written about it, and if you look at some of these, especially these hobbyist books, they tend to be about Xilinx. So I was tempted, and then I heard that Vivado is extra crappy, and I was like, okay, I don't think I want extra crappy. So I just went the regular crappy Quartus Prime. And in fact, the IDE is really bad. I ended up just editing outside and using it just as a compiler. So I would just switch back and hit compile, and that's kind of the only thing I did. It's pretty deep. You can really find out a lot about what you just built. So at the end, you get this really long report, just hundreds and hundreds of pages of lines of report, stuff like, did you violate any of these timing rules? How many of these multipliers did you use? How much RAM did you use? And it can go on for a long time. It's pretty useful, and I think if I were a real engineer, I would probably get into that and really look at that carefully. But for me, I basically got an FPGA that was much too big for me, so it was fine. Like I just didn't need to worry about it.
What was the problem with a virtual machine with VM?
Mostly it was a problem with USB, because every time I went to like do something with USB, we get disconnected, and then the IDE doesn't deal with USB getting disconnected, and then you have to reconfigure it from scratch every time you're doing anything. I found it easier just to reboot, and then it just. Yeah, that's true. That's right. So, oh yeah, very good. So these things use up a lot of RAM, and on an 8 gig machine, that was not going to work side by side with macOS. So you just do the right thing and just reboot into Windows. The enclosure looks like this. It's very cool. We made a laser cut acrylic enclosure as a test. So here's a picture of it. So it's kind of hard to see, but it's like 2 slices of acrylic that we laser cut. So the display is on top, standoffs to separate them, and then just the meat in the middle. And that gave us. Which machine you mean? I use TechShop's laser cut. Yeah, I almost made a joke about Chris's laser cut acrylic now. And that was really good. It was a university. Yeah. So that was really good for giving us a sense of like, is this going to work? Is it going to feel good? How does the accelerometer work? It turns out like the accelerometer did not work well because it's too slow and too, like you turn it, it takes a while for it, because it's either really noisy or you have to average a lot of samples to get rid of the noise, and then it's too slow, and then when you move it, you don't get instantaneous response. And we want to do stuff like as you move it, you get parallax response. So that got us to add a gyroscope on our final version. So that was really good to do, and useful just all around to prototype it. And then let me go back to this. So the final one was designed with Fusion 360, which is a free program. Well, it's available for free by Autodesk. It's a very good 3D modeling software. And then I printed with my friend Jim's 3D printer. I want to shout out to these heat set inserts, which I didn't know about until I started working on this. And when we open this, I can show you what they look like. But the little brass pieces like this, they're basically the nut part of a thing. So they're available in M1s and M2s and M3s or whatever. And then they got these little knurls on the side. So you 3D print a hole for the nut that's slightly just the right size so that they sort of half fit in there. And then you stick your soldering iron into it, which conducts the heat through the brass, slightly melts the PLA or whatever it is you're using. You go into it and you pull it out and it solidifies. And then you get an actual nut that you can screw into many times, because otherwise people are tempted to make a hole that's just the right size in PLA, and you do that like 4 times and it strips and it doesn't work anymore. So that was super cool, and we used them all over the place. And you can see them when I open this one. This is sort of halfway building this. You can see the LCDs being trapped in by these 4 clips. And again, I used the heat set inserts there to hold that. And here's the button. This red button is just like the home button on an iPhone. Like when you go into demo, you can click it just to go back out to the menu. And that's the only thing it's used for. And you can see the capacitor there for debouncing.
The interface on the screen, is that just like a round column thing or a spy or what?
For touch?
No, for the actual video part. You said you would
How do you, I mean, like when you're sending video to it?
Yeah.
So it's the same as VGA, it turns out. So it wants the the horizontal retrace and the vertical retrace, and it's got 2 pins for that. And and it's just like VGA, except that instead of analog, you give it 24 pins of RGB. And it's clocked because it's synchronous. So it doesn't have to guess what your clock rate is. You're actually like for every single pixel, you give it a clock and say now's a pixel, now's a pixel.
Is it evenly spaced or is it more green bits? Or
No, it's 888. Yeah.
It's actually not common with video, right? So
Yeah, this is pretty high. This is a lot of color resolution. Yeah, sometimes it can be like 16, right? And then they'll do like 565 or something. No, but this was 24.
We ended up using, of the pins on the device, like 30 of them just to get the video to the
Yeah.
LCD.
Yeah, that's right. That's right. But timing it was nice because I already had a VGA output from the previous dev board, so it was nice I could just adapt it pretty easily to this. And then you can use all sorts of things. But it's very flexible about what it accepts. Like we have 50 FPS because the 50 megahertz, if you work out like the clock, the dot clock or whatever, it works out to about 50 megahertz, 49 point something. But it works fine at 50. It works at anything. It's not very picky. It's just like every time you give it a pixel, it just updates it. And you need to do it fast enough that you don't lose the image. But it takes several seconds for the image to lose, so you're not in a hurry. You could go at it pretty low.
Diving a little bit deeper, I'm curious. If I bought one of these from eBay, I'd be tempted to go Googling to see if anybody got a sample Verilog code.
Yeah.
Did you start with the non-readable documentation? Was English, or did you find
Right.
sample source?
It's a combination of both. So I already had the VGA, which had come from the demo code that came with the previous dev board, the DE0. And so I kind of had that already. And then when I started looking into LCDs, it turns out it's similar, so that was good, so I could adapt it. I had to add a clock and a few other things. But also, like you said, like the manual for these things is not awesome. And there's a different mode where instead of giving like horizontal and vertical retrace, you have like a data enable pin or something, which is very badly documented. But this is what I ended up using to save myself a pin. And instead of like giving it a weird horizontal and vertical retrace, which is basically a backward compatible mode with VGAs, every time you have a pixel, you say now. And then you just give it a look, you take a break at the horizontal and vertical, and that's how it knows where everything is. But it was sort of a mixture of the two for that, for sure. Okay, so the board itself does almost everything we needed, but we need a few other things. A battery charger and a discharger, the whole like logic of like charging a battery and then getting it back and monitoring the battery. So that's an Adafruit board. The LCD driver, driving the LCD itself, the data is fine. You can just take that straight from the FPGA, but you need something to drive the backlight. And the backlight is a constant current LED, so you need an LCD driver for that. That's also, I don't know, either Adafruit or SparkFun, I can't remember. We added a gyro sensor because we learned that we wanted really fast response on moving.
Was the gyro sensor, is that just I2C?
Yeah, yeah, exactly. and a touchscreen controller, which was also I2C. So the touchscreen gives 4 analog pins, and they're bidirectional analog. It's kind of weird. The way that you set up a voltage, and then you read it. It's kind of complicated. So instead of doing all this ourselves, you just buy an Adafruit board, and you plug in the analog, and then you get the I2C that just tells you where this. Was it? What?
Is it resistive?
Yeah.
Touchscreen?
Yeah. Yeah, which is kind of annoying because everybody uses capacitive, so they'll touch it with their finger, but actually that's not great for resistive. So like most of the taps don't work, and we tell people to do it with a thumbnail, and that works a lot better. And even if you tell people that, they'll do it once, and the next tap they'll go back to their finger. It's just too much. It's really hard to switch to that. Right. So version 1 used Adafruit boards, which was okay. So here's. Yeah, so this, I can pass it, afterwards we'll see it, but basically it's a board that has a bunch of long sequences of, what?
Oh, there's another one you can pass it in. There's a whole stack, right?
Yeah, but that's the new one.
Oh, these are the new ones.
So the old one had like a bunch of long, like 20-pin through-hole stuff, and all the Adafruit boards were plugged into that and soldered, so it was more of an assembly kind of situation. And then for version 2, we tried to incorporate all these boards directly onto our daughter board. And that was kind of half success. I think we got the gyro on there, and then we got everything actually except for battery charger. We got the LCD driver was still a separate piece, I think.
Yeah.
And then yeah. So
We incorporated the LCD, we incorporated the gyro and the touchscreen.
that's right.
But then we didn't get the battery charger to work because it's analog and I suck at analog.
Right. So we still needed to go back and use the Adafruit charging board for that as a separate board, but you can sort of see, and there's a populated version here that you can look at. But that was sort of the only real like hardware that we did, and Brad did all that in KiCad, had it manufactured in China. This is kind of I don't know if people here have manufactured PCBs, but yeah, anybody? But like traditionally here it was OshPark was the famous one. It's like open source hardware. They're in like Portland, I think. And that's what we had been using for a long time. They're known for their purple boards. If you've ever seen a purple board, it's OshPark. And then for here, we tried, okay, well, let's just try this Chinese company. And it was like half the price and got here a lot faster, despite.
LPCB or somebody else?
It was, which one?
Oh, PCB.
PCB Way, yeah, that's right. Yeah, yeah. I've tried them too. I've tried the JCL PCB, but like. PCB Way was like insane. It was like Brad sent it out on Sunday to them, and on Thursday it was in San Jose. Like they had manufactured it and shipped it for like much less money than OshPark. And
What kind of money was it?
Tens of dollars.
for maybe 5 or 10 boards.
You can actually get them shipped faster too.
Yeah.
What's nice is they have a liaison, so as soon as you upload, they want to verify it and talk to you about it.
Yeah.
Which is really nice too. And they're like 2 weeks overnight.
Yeah.
That's true. So
Yeah.
you go to sleep, and then in the morning you get questions. So you can
Yeah, it's basically like it's free, right? It's like it's so little money. It's like there's no way it's worth doing anything else. It's tens of dollars for like 5 boards, right? It's not a board, and so it's just.
There's 3 normally with Osh, right?
Yeah, that's right. It's 3 with Osh, and it would be probably at least 50% more expensive.
It becomes very noticeable when you have bigger boards.
Yeah.
PCB Way stuff I didn't design it. It was some Amiga graphics card.
Yeah.
And the size of the unit came to about $60, whereas if I'd gone to Osh,
Yeah.
it would have been way over 100 and
Yeah.
something.
Yeah,
And
it's.
I got 5, not 3.
Yeah, that's right. And yeah, it's by the square inch, and it's like $5 at Osh, so it like it quickly blows up for sure.
JLC BCB currently is running a promotion.
Yeah.
$2 for 10 boards.
Yeah,
To my understanding, they don't actually manufacture it. It's more of a marketplace.
yeah,
So
Yeah, they find somebody to do
you
it.
will not get PCB Way. I think is more consistent.
I think that promotion is under a certain size too, but it's still a pretty
Yeah, 10 by 10, I think, centimeters.
centimeters. Yeah, that's right. So it's still pretty usable size. Like we could have done it for sure. This is what the populated V2 looks like.
This is actually putting it into the oven, so you can see it.
Oh, right.
A little bit,
Right.
sideways, but
Yeah, yeah. When we do the LS3 talk, we'll talk about like manufacturing these things because that's a whole adventure in itself. But we do that just in a toaster oven. And here's sort of, so this is pretty fun. So as I was designing all this in Fusion 360, one of the things that I did is that I modeled the daughter board. And then I was trying to make sure that it was like going to pass and then the LCD wasn't going to run into it and stuff. But because I had it modeled, I could 3D print it. And then when I put it together, I could actually put it next to where it's going to be and make sure that it was going to fit and not hit any of the other connectors on the dev board. Okay, tools. Google Doc, of course, for everything. We ended up with a 43-page document with all of our design ideas and everything. I know, right? Yeah, it's like everything, how to boot Linux and just everything that we learned, we would put into this doc. GitHub, of course. KiCad for the PCB design, Fusion 360, PCB wafer manufacturing, and WaveDrum. So WaveDrum is kind of magical. So the when I was doing this, I really had a hard time thinking about signals and coordination between signals. And there were all these tools online where you could sort of draw these signaling diagrams like you see. But like screw that, I'm not going to draw things. I'm a programmer, I want a text file. So I thought, okay, I just want like a JSON document that describes the stuff, and it generates like a beautiful thing. I'm going to write this. This is totally awesome. And I'm like, wait, I've seen this before. If it's that awesome, it's got to exist. And sure enough, I Googled, and WaveDrum is like, so it's better than anything I could have made. It's like, it's beautiful, it's super flexible. You can embed it in your web pages. So like my web page for Alice 4 has these things, and they're generated on the fly in your browser. So they're really high res and good looking. And basically, you just give all your signals and what they're doing, and they just make one of these things. And it's one of those things where like I was just constantly surprised. Will my mouse work? Yeah. So like I just couldn't get into my head like, okay, if I set a variable, A or register A on this clock, it's not available until the next one. And I couldn't get that into my head even after months. And it was super useful to see here, for example, I don't know if you can see these dashed lines correspond to the clock. So this is the up arrow here is the positive edge of the clock. So for example, if I set FIFO read to on at this clock, afterward you see the rising thing. And that was super useful for me visually to truly get into my head like it's after the clock that it goes up and not before, and it's readable here. And if it's changed back, then it goes back. I don't know if you can see no, not so much? Okay. But it was useful all these things are different kinds of data that are being passed around, and like I couldn't have done it without WaveDrum. If you get into FPGA programming at all, like definitely recommend writing a bunch of these things, and just to clarify in your head what is actually happening, because debugging these things is hard. Performance. Bart was asking about performance. So 50 million pixels per second, and about 2 million triangles per second. There's a Brad side on the arm is about 2 million, and then on the pixel side it's about 50 million. So we think it's an early 90s SGI, but I think by early 90s they typically had texture mapping. So maybe, which we don't have at all. So maybe it's not a super fair comparison, but it's performance. I think that's right.
Cost a lot of money.
So it's kind of crazy that two software guys who don't know anything about this can make like what probably took tens of engineers and cost tens of thousands of dollars. But that's how good FPGA stuff
To
has
be
been.
fair, I mean, we did do a lot of graphics network in the graphics group at ARM. But we did, I mean, it wasn't like in spare time you could do this. And then beat the 25-year-old computer.
Yeah.
Have you guys ever tried to actually compare it to an Indigo 2?
Like actually run it? No. Do we have one?
At VCF West, we had an actual
Oh yeah. A personal iris, right?
yeah, the personal iris running it, and it was substantially faster than the personal iris.
That's right. Yeah, we
Personal Iris is significantly older, though, right?
late.
92, 93, or ish.
I think his would have been 89.
But the graphics side, I think, was slower.
I don't know. I don't remember. Yeah. Yeah.
That's right.
But it was. Yeah. Exactly.
Well, I have an Indigo 2 if you guys ever want to do.
Oh.
I have several, actually.
Oh.
You can have one.
I'm good, thank you.
We're all full of.
Is it in a LAN or is it an impact?
Multiple.
Do you have multiple different ones?
Most of them
We
are
could do like
impacts.
a spectrum test.
Most of them are impacts.
Yeah, so those will be probably faster plus higher res.
Yeah.
So the kicker of all this is like so that little spider demo that we'll see later is the first real-time 3D I ever saw. So I had done all sorts of 3D. It was 30 seconds per frame or whatever, like on my PC on the EGA or whatever. And then, but one day I went over to a friend's house or friend's work, and he had an SGI, and I saw this graphics spider walking, and it utterly blew my mind. And a lot of this stuff has been trying to recapture that. And so getting the C source code of all these demos, all of these C files at the top say written by Thant Tessman. So he was clearly the dude at SGI who wrote a lot of these demos. So we're at VCF West, and I emailed the guy. I'm like, hey, I'm going to be at VCF West, just to let you know. And he shows up, and it's this dude here on the right. And this is the guy who like wrote all of these demos that we, like, I don't even know what's going on in his head if he's thinking like, I wrote these demos 30 years ago, and these guys made a hardware machine that does nothing but run my demos. That's all it does. And his kid was there, and we were all like fawning over the guy. And his kid was like, "What? He's just my dad." And the whole thing was just weird. The whole thing was just kind of surreal, but it was really bizarre. But I loved that so much. Okay, so I like this because when I look at all of these projects, they seem so smooth, right? It's like somebody has an idea and it works in their basement, and an awesome thing comes out. And then even when I think back, my own memory of the Alice 4 is that it was that way. But then preparing this slide deck, I went through a lot of the emails, and like it wasn't clear at all, right? And we're like, I don't know which way to do it. I don't know which provider to use. Xilinx or thing. It's like I feel like I should get an agile, you need like an actual education with actual knowledge, and I was totally intimidated. And then somehow just powered through and did it. But like it was good for me to see that again and realize like, oh no, next time I get stuck, yeah, that just happens. You just need to go. And I think it's so easy for people to sort of forget that was part of it. And when they're presenting it, they're like, oh, and then I did A, and then I did B, and then I did C, and then hardware comes out. And it's not like that at all. It's like there's horrible parts in the middle where you really don't know what to do, and if you're going to take a fork, you're going to pick wrong, and then you use Vivado or something, which is awful, and instead of the other one. Okay, lessons. Real quick, if you're actually interested in doing this, synchronous DRAM, like I said before, has all this variable latency. It's really hard to use. There's on-chip static RAM that you can just access in one clock cycle. So I didn't do this, but I would probably move a lot of the SDRAM stuff onto the chip, do work there, and move it back out. And then most of the code there doesn't have to deal with this variable latency. And if you can do that, you try all you can. And in fact, I think GPUs pretty much do that, like real GPUs do that. And what they do is they work on small tiles, like 64 by 64 tiles. And then whatever memory they need for that, they bring it in. They do everything for the tile entirely in SRAM, or as much as possible, and then they spew it back out. And then they go on to the next tile. Instead of like, so if you have a big triangle, you sort of break it up into little tiles and you do it one at a time. And then you don't have to worry about any of this like variable latency, static DRAM. Synchronous DRAM. Single clock. So I think you said, like, can you have multiple clocks? Okay, so they have phase lock loops, which are this hardware thing that you can use to take any clock into any other clock. And so you can do that. You could say, let's say this part works really well at 50 megahertz, but let's say this other part can run as fast as 74. So let me use a PLL, go up to 74 megahertz for this part, and then it'll run like 50% faster or something. You can do that. It'll totally work. Or another example would be, for example, you want to go out VGA at 640 by 480, and the clock for the VGA is like 25.8 megahertz or something. So you use a PLL to generate that, and a bunch of your logic runs at VGA speed instead of like computation speed. So it's generally a really bad idea, and the reason's kind of obscure, and I can tell you later over dinner if you want to, but basically it goes back to like you have that B plus C on the right-hand side. It's going to be ready. It's going to be latched into A. The compiler will know for sure if those two are the same clocks, that it'll work. But if those two are in different clocks, like you're generating data here and then you're consuming it here, then it might latch right when it changes. And if it does that, the flip-flop will do what's called go metastable. And then so you have to do all this work to get around that. And if you don't do that, then your flip-flops will have garbage in it a lot of the time. So what you want to do instead is run your whole FPGA off of one clock. So let's say you think, okay, I need this thing is at 50 megahertz, this other thing is at 75 megahertz. Generate 150 megahertz. And then for this whole part, you do something one cycle out of 3. And for this part, you do something one cycle out of 2. So you end up with the right speed, but they're all completely synchronized. And anything that goes across will actually be on the same clock. And that's like, so you do, you have a tick, which is true 1 out of n, depending on what you're going to do.
Does this have a name, like hierarchical clock or something?
Hierarchical clock is different. That's a different problem where you want as much on the FPGA as possible to clock at the same time, but clock actually has a propagation delay. So you want to make sure that you have like a tree of clocks so that everything happens almost at exactly the same time throughout the FPGA. I don't know what the name of this is, but basically, like if you're tempted to use a PLL resist and try to find a way, like a least common multiple or whatever of all your different clocks, and just use ticks to actually to slow down the different parts. And what you can say is if tick, right, and that's true 1 out of 3, anything in the middle will actually happen 1 time out of 3 clocks. So it'll happen at 50 megahertz even though your actual clock is running at 150. And okay, so lesson 3 is like, so I read a lot of stuff about hardware manufacturer engineers, and they all say like, yeah, we don't actually send the stuff to the real chip. Like, no, we simulate, and that's because when you work on real designs, it doesn't take a few minutes to compile. It takes like hours, sometimes like 20 hours to compile. So you can't make a small change and compile and try it. You have to run it in simulation. So they make these small modules, they simulate until it's perfect, and then they assemble it all. And they do all that in simulation, and then they try it on the real hardware. I didn't listen to them because I just tend to just want to run stuff and I'm impatient. So I ran everything on the real hardware the whole time. And when I started, compiling took about 2 minutes. And by the time I was finished and I had a lot more in it, it was about 7 minutes, which is a pretty long term. Like you hit compile and you go read it or whatever. It's like it really slows down your compilation. I recommend Verilator if you want to do it. Like I said, all the open source tools are Verilog, so stay away from VHDL as a language. Verilog has lots of support. Verilator is really good. It actually compiles your Verilog to C++, which runs very fast. It's about 100 times slower than hardware for what I was doing. It's easy to debug and stuff like that. So definitely go down that route instead of spending 2 minutes for every recompile. A lot of other details, whatever. Right, yeah, one more thing about Verilog is there's a Verilog spec, and it tells you how to so the history of Verilog is that they did it first for humans to consume, and then they wrote simulators to simulate the hardware, and only later did they actually use it to actually synthesize hardware. So when they were in the simulation phase, they wrote all this spec about what simulating Verilog means, and it's a very specific spec. Unfortunately, it doesn't match what happens later with synthesis. So it's very easy when you're writing Verilog to do what's called this mismatch between synthesis and simulation. So it's one of those things where like you can do something, if you're going to go down the road of simulating, you can do something that works really well in simulation and then it won't work. And then a lot of the books that you read are like, yeah, don't do that. Like write it in this one way so that it'll work the same way in both. Verilog, to its credit, actually behaves more like synthesis. So you're less likely to run into that problem if you do that. And that's it. So all this source code is on GitHub, and there's a write-up. Yeah, that first thing is a write-up. It's pretty detailed. It's got 2 sub-pages for like the hardware and the software part, but also pretty high-level overview with pictures. And then here's our contact info if you want to follow up with questions or whatever.
Question.
Yeah.
So on the RSGL side, how complete is your implementation? His implementation?
Not very complete.
So the good thing about
Just enough to get the demos to actually work.
Pretty much. Yeah.
So the good thing about the demos, and this is actually a pretty key thing about having software that's ready to go, is we sorted them by how much of the API they used. And it turns out that like that walking thing, which is called Insect, doesn't use lighting, even though it has shadows, because it fakes its own shadows and fakes its own lighting, all internally to the software. So we did that first because we didn't have to get any of the lighting stuff to work. And then we moved on to the next one that had lighting, and then we moved to the next one that had stippling, and then so we could order them that way.
Increase in complexity.
Complexity and API stuff, and then when we got to the end, we stopped. So we don't actually know what's left, but presumably there's like more stuff. Well, they added stuff to RSGL like textures that we don't support at all, clearly.
We've got 2 different variants of RSGL as well, different ways of providing vertex data. And so we actually have 2 sort of different flavors of RSGL we support.
Mm-hmm.
Like there was a polygon style, and then there was what they call B3F style.
Yeah.
So we don't cover a lot of stuff. Like you
Yeah.
can do menus, and we wrote a little bit of code to do menus, but we never finally
Yeah.
put that into the machine.
Yeah.
There's all the stuff you can do with RSGL that we don't provide.
Yeah, I think we think that the C files we got are from the late 80s. So it's probably, I bet that the demos were pretty current. We used a lot of the thing because they're demos, right? So they want to push the boundary of what they used. So it's probably late 80s RSGL. So it's pre-texture mapping, pre any of the stuff that they added after that. But it wasn't very long after that that they switched to OpenGL. So yeah. Yeah.
The triangle forward that's there communicated from the Linux RSGL side to the raster.
Yeah.
Is that just string coordinates and integers?
Yeah.
Okay.
Yeah, there's a couple bits in there for subpixel fixed point, but we never used it. But it was that. It was yeah. Yeah.
We did some tests, and we sort of couldn't tell the difference.
That's right. That was a good thing about the Mac OS version, is that we could do a lot of testing on the Mac OS version because it used the same algorithm that I said about testing each pixel on the inside out. So that was a good thing. We wrote it in integer rasterizer that did the exact same algorithm. Then we could do tests. Does subpixel positioning help? No. Okay, don't do that then. Yeah.
I remember you guys talking about that about the L3 as well, but building an emulator
Yeah.
to
for sure. Absolutely, yeah.
There's some other ways we cheated. We don't draw actual lines, we draw really thin rectangles.
Yeah, yeah, that's right.
And we don't draw points, we draw really small rectangles.
Yeah. And fonts are like, every pixel is 2 triangles or some crazy thing, yeah. So there's a couple of these things that have writing on it, and like every single pixel of the font is 2 triangles.
This is the crazy thing about it. I mean, it's like every glyph in the font is little pixels that we're drawing with little triangles, and yet it's so fast that
Yeah, it works fine, yeah.
we don't have to care.
Yeah, yeah.
What does Alice stand for?
I came up with the name because I liked Alice in Wonderland, because I think when you were working with Alan, you just didn't have a name. I'm like, what should we call it? I'm like, Alice. I don't know. It's like one of those like sophomoric obsessions with Alice in Wonderland, and then I was like, Alice, and so it stuck.
We weren't dating anybody in Alice
No.
at the time, so it was like,
No.
oh, it's not anyone in particular's girlfriend.
Yeah.
And then
Oh,
my wife is named Alice.
yeah, exactly. Yeah.
Years later.
So what were you doing at SGI when you were there? You did 2 stints?
The first stint was scene graphs, where I worked on Performer, and the second stint was applications engineering, so just kind of going on site and helping people.
Anything else?
Didn't you were an intern
I was an intern, yeah.
working on what became the N64?
The Nintendo 64, that's right. Yeah, that was designed by SGI. Yeah, so that was an internship. Yeah. Yeah.
At the very beginning, you said that you worked on the Mac BSD.
Yeah.
Just curious, but was like was it the was like a real operating system or like an environment? So was it running on top of Mac OS, or was just booting the machine like
Yeah.
IUX?
Yeah.
These tools?
It was like AUX.
Yeah, so the Mac 2 that we had an MMU, but it wasn't used by Mac OS. So any user land program in Mac OS could just do whatever it wanted. So yeah, so that you would boot into Mac OS, and you would say, I want to boot thing, and you would point it to the partition, and it would malloc the kernel, load it into it, set up all the MMU tables to pretend that that's 0, and then turn on the MMU and simultaneously just run to the thing.
So
Yeah.
everything else was in Mac OS was just gone.
Yeah,
so
it was blown away.
what
Yeah.
left was us, and we took control.
Yeah, I think it's the
It's
same
like when you
trick
boot-
used by AUX.
Yeah, it's this kind of thing like you boot it on Amiga or something.
Yeah,
You boot it from the Amiga OS side,
And that's
then
Yeah.
yeah,
Yeah.
it's gone.
yeah.
It was never well. I mean, I was going to say it was never super strong on the hardware, but it was good enough to last for 25 years.
Yeah. Yeah.
Do you still have the sources? Are the sources available or
Of Mac BSD?
or Mac BSD? Yeah,
Well,
The C, well, it's of the BSD, you mean? Yeah. So it's NetBSD. It's the port. It's a Mac 68K port of NetBSD.
Their names don't copyright this.
Yeah. Bizarrely.
okay, but you have an old version because do you have the old version you worked on with it?
The original.
Yeah.
No.
I don't think we have anything that can be identified as Mac BSD.
No. We stopped working on the project in the mid '90s, and so we don't have it.
I have some stuff that has our names in it and
Yeah.
weird comments that I'm sure
Yeah.
we did later, so I
Yeah.
want a piece of it.
Yeah, bizarrely, somebody took something from that project and did something with it, and through a route that we don't know, it ended up at Apple, and they used it in iOS. And so if you look at your iPhone, and there's a copyright, like a super long copyright page, in the middle of it, like Brad and I are in there. And we don't know why. We're certain that there's nothing left, right? Not a single bit that we wrote is in there, but the lawyers are conservative, they're like, sure. We'll spend 100 bytes to stick their names in there, because I don't want to have to track down whether or not it's...
You don't have also something that is running that you can install on, I don't know, Mac 2 or 2FX and see what happens.
I think if we were going to do that, we'd probably start over again with NetBSD Mac 68K, pull those bits down, follow whatever process is current for that. Like I don't think I have anything. We might know someone who has those bits sitting around.
What are you looking for? You're looking for an early version of
I think
NetBSD?
you're asking for like an original version of Mac BSD that you could run on like a Mac 2.
Yeah, exactly, 68,000. Because I know that then later they also moved, because I remember I was using it before Mac OS 10 on my MacBook, or my PowerBook, on a PowerBook G3, on a Gizmo machine. I had this Linux, that was called Mac 68, no, even, I'm making confusion, it was 20 years ago. There was Mac 68,000, Mac 68, Mac 68K.
Linux 68K.
Sorry, Linux, sorry, not Mac. Linux 68K. And that was for 68,000 machines. And I think I installed it, I don't remember where. And then I had another version for PowerPC because it was running on my PowerBook G3 Pismo. No, the black one. I still have it. Yeah. That would be interesting. I would expect, you can put on, I don't know, on Macintosh Garden or possibly. Well,
Yeah. Any other questions?
that's it.
Great. Thanks. Yeah.